Dear students, good evening and welcome to this episode of JEE Main Revision organized by RACE. And today we will have a few chapters in organic chemistry, haloalkanes and haloarenes, alcohols, phenols and ethers. As usual, we have 25 questions. 20 questions multiple choice objective type questions and 5 questions single digit answer type questions, and the total time allotted is 2 hours and 30 minutes, and let us try our best to cover all the questions in the allotted time. So coming to the first question, in the following sequence of reactions the compound C is formed. So there is a reaction of an amino compound, a primary amine, the reaction with the nitrous acid to give the compound A, which on oxidation gives the compound B, and the compound B is reacted upon with methyl magnesium bromide, the Grignard's reagent, followed by hydrolysis of the compound in acid medium to give product C. So what is the product C is a question. So you have to identify the product C. So for that you must know the sequence of reactions. Of course it is not a difficult substrate, it is just 2-amino propane, and you must know the reaction with the nitrous acid. In the chemistry of nitrogen containing organic compounds, you might have studied that aliphatic primary amine reacts with the nitrous acid to give an unstable diazonium salt which spontaneously decomposes to give the alcohol as a product. So the product A is an alcohol. You must also remember that if it were an aromatic primary amine, it would have reacted with the nitrous acid to give again a diazonium salt which is fairly stable. In this case, the diazonium salt is unstable and spontaneously decomposes to the alcohol. I can formulate the reaction like this: CH3, CH, NH2, CH3. So here is the diazonium salt formation, that is the N triple bond N positive Cl minus, and on this reaction with H2O, this compound, the substrate has CH3, CH, CH3 here. I have now written that CH3, CH, CH3. This is the unstable diazonium salt. It decomposes with water, very easily decomposes with water to give the compound CH3, CH, CH3, OH. So the total chemistry is the conversion of the NH2 group into an OH group. In the place of the NH2 group, you are getting an OH group. That is the net result of the reaction. But remember that it proceeds through the formation of the intermediate diazonium chloride, which is unstable, the diazonium salt which is unstable. Okay. So you have the compound A, which is isopropyl alcohol, a secondary alcohol, you know that, and a secondary alcohol on oxidation. Oxidation of the secondary alcohol, you might have studied this reaction. I hope all of you remember this reaction. Secondary alcohol on oxidation gives a ketone. If it were a primary alcohol, then it would have given an aldehyde as a product. The primary alcohol on oxidation gives an aldehyde. A secondary alcohol on oxidation gives a ketone. So in this case, the product is a ketone. So that's the product B. So the product A is isopropyl alcohol, and the product B is acetone, a ketone. Now this ketone is reacted with methyl magnesium bromide. So again you have a very interesting chemistry, that if it's an aldehyde, it adds one molecule of Grignard reagent to give a product which on a hydrolysis will give a primary alcohol, whereas a ketone will add one molecule of Grignard reagent like this to give CH3, CH3. Already there are 2 CH3 there, and this CH3Br will be added to the carbonyl group to form this compound. It's a nucleophilic addition, as you know. Double bonded compounds like carbonyl compounds, not all double bonded compounds, carbonyl compounds, C double bond O compounds are characterized by nucleophilic addition reactions. And here this methyl magnesium bromide provides a nucleophile CH3 minus, because you know that the methyl magnesium bromide, the metal atom has positive charge and CH3 has negative charge. So methyl bromide, magnesium bromide is providing the nucleophile CH3 minus, and that is getting added to the carbonyl group to this compound, and this compound on hydrolysis, HOH, you are getting CH3, 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 COH. That means you are getting the compound 1, 2, 3. You are getting 2-methyl propane 2-methyl propane 2-ol. So the answer is 2-methyl propane 2-ol. You have to specifically give it as propane 2-ol. It's a tertiary alcohol that you get. A ketone on adding Grignard reagent gives a tertiary alcohol. Actually, the statements are like this. Formaldehyde reacts with a Grignard reagent to give a primary alcohol. Other aldehydes react with the Grignard reagent to give secondary alcohols, and ketones react with the Grignard reagent to give tertiary alcohol. So in this case, you get a tertiary alcohol which contains all the three alkyl groups as methyl groups, because the acetone had 2 methyl groups in it, and now you are adding 1 methyl group. That means you are getting the alcohol where the carbon atom has 3 methyl groups and OH group on the carbon atom. So it means the product is 2-methyl propane 2-ol. So the correct option is C. C is the correct option, 2-methyl propane 2-ol. So you find that it's a sequence of reactions. The reaction of a primary amine with a nitrous acid to give an unstable diazonium salt, decompose to give an alcohol, in this case isopropyl alcohol, and on oxidation, isopropyl alcohol being a secondary alcohol, it is oxidized to a ketone, and this ketone on adding methyl magnesium bromide gives an addition compound which is hydrolyzed and to give 2-methyl propane 2-ol. Okay, so that is the first question. I think it is clear. Now this is the second question. So look at the substrate. Okay, what is the compound? Look at the compound very carefully, and the reaction is reduction by lithium aluminum hydride. Of course, when you see the reagent lithium aluminum hydride, we know that lithium hydrogen aluminum hydride is a powerful reducing agent, and there is an analogous compound sodium borohydride, but the reactivity of sodium borohydride is slightly less than that of lithium aluminum hydride. So there is difference in the reducing capacities of lithium aluminum hydride and sodium borohydride. You must have studied that. And here the reduction is with the lithium aluminum hydride. So what does this lithium aluminum hydride do on this molecule? So looking at the molecule, one can easily understand that here there is an ester group. Here is an ester group, and at this part there is a group, and this group is actually the group formed by a reaction like this. So you have that CHO, CH2, CH2, CH2O structure here. This is a structure. So this structure is a structure obtained by the reaction of an aldehyde with a glycol. You might have studied this reaction while we discuss the chemistry of aldehydes and ketones. The reaction of the aldehyde group with a glycol. Actually, this reaction with a glycol or the aldehyde or ketone is a method of protecting the aldehyde group or keto group. So that sort of a group has been generated here in this compound, and now the lithium aluminum hydride is used to reduce this compound. The reduction of the ester group to a primary alcoholic group, ester is reduced to a primary alcohol by lithium aluminum hydride. That is one point that you have to note. And this cyclic structure here which was originally generated in this compound by the reaction with an aldehyde and glycol. This part of the molecule is also reduced by lithium aluminum hydride, to this part is actually reduced by the lithium aluminum hydride to form a compound like this, OH, OH. That's the compound formed, and as you know, a water molecule is eliminated because normally a compound which contains two OH group on the same carbon atom is unstable, which means you have a hydrogen atom here and the CHO group is regenerated at this point. So this cyclic structure here on reduction with the lithium aluminum hydride will give back the aldehyde group. That's the point. You will get back the aldehyde group, and this ester group on reduction will give a primary alcohol. So the product of the reaction is one in which the ester group has been converted into primary alcohol. Remember that lithium aluminum hydride will reduce ester to primary alcohol. That is something that you have to keep in your mind. Ester is reduced to primary alcohol, and this part of the molecule, which I told you, is a part which was generated in this molecule by this sort of a reaction, is getting converted back into the aldehyde group on reduction with lithium aluminum hydride. Okay, so the product of the reaction is one having a CHO group at one point and the CH2OH group at the other point. That means the correct choice of the reaction is B. B is the correct choice of the reaction, which has a primary alcoholic group at one point and the aldehyde group at the other point. Okay, a good example, one must know. Particularly, students may face some difficulty with this part of the molecule. So remember that this part is a part of the molecule which was originally generated in the molecule by this sort of a reaction, and on reaction with the lithium aluminum hydride, the interesting thing is that the original aldehyde group is got back at the same position. So the final product is one where this group is converted to the aldehyde group and this group is converted into the primary alcoholic group. So that's the job done by lithium aluminum hydride. Okay. Now there is a comparatively very simple question. Which of the following reactions will produce primary alcohol? Hydration of propene. I hope all of you can predict what would be the product when propene is hydrated in the presence of dilute sulfuric acid. It is a Marconic of addition of water in the presence of protons, acid catalyzed. So you can simply formulate the reaction like this for simplicity, and the product is CH3CHOH-CH3. It's not a primary alcohol, it's a secondary alcohol. So that means option 1 is not correct. Now what about the second option? The second option is reaction of propene with diborane. It is simply given as borane. So the simplest borane is diborane. So diborane can react, B2H6 can react with this compound. You might have studied the hydroboration reaction. It is the addition of borane in an anti-Marconic manner. But however, the product that you get by the addition of borane has to be oxidized by alkaline hydrogen peroxide to get the alcohol as a product. That means the alcohol is obtained as a product only when we do the two reactions, namely hydroboration, that is the reaction with diborane, and the second part of the reaction is oxidation, which requires alkaline hydrogen peroxide. But here that is not given. Here what is given is reaction of propene with borane followed by water. Of course, water cannot oxidize that compound obtained by the addition of borane to this double bond. Okay, the product actually obtained would be CH3, CH2 thrice B, that is tripropyl boron. That's the compound formed in this step of the reaction. Okay, but this compound is not oxidized simply by water. For this compound to be oxidized into a primary alcohol, CH3CH2 CH2OH, you require an oxidizing agent, and that is alkaline hydrogen peroxide. And the two reactions together is very famous and is known as hydroboration oxidation, corresponding to anti-Markovnikov addition. That is the importance of the reaction. You might have studied that the hydroboration oxidation is a regioselective as well as stereoselective reaction, because it is specifically anti-Markovnikov addition of water to the double bond that is happening as the total outcome of this reaction, that is hydroboration oxidation. So anyway, it is water here instead of hydrogen peroxide alkaline, and therefore the reaction B will not work to give normal propyl alcohol. So B is ruled out. Now what about the third? The third we have already seen, propanone or a ketone with methyl magnesium bromide followed by hydrolysis. In the previous example we have already seen that the product obtained would be a tertiary alcohol. So the option C is also not correct, and the only remaining option is D, and let us see whether D is correct or not. It is catalytic reduction of butanol. Catalytic reduction of butanol. Butanol is an aldehyde. An aldehyde on reduction by hydrogen in the presence of a catalyst like nickel, for example, or a catalyst like palladium, for example, or even platinum as a catalyst. A metal catalyst like this, one of these, will reduce this compound CHO to CH3, CH2, CH2, CH2OH. That's a very simple reaction which is already known to you. Aldehydes are reduced to primary alcohol. So aldehydes are reduced to primary alcohol. So the catalytic reduction of butanol is the correct option for this question. I hope you understand. So you have to rule out A, B, C. So you must know the chemistry in A, chemistry in B, chemistry in C, and you can rule out those reactions and quote this reaction, catalytic reduction of butanol, which is very straightforward answer. Butanol is an aldehyde. On reduction by hydrogen in the presence of a catalyst, the aldehyde group is reduced to a primary alcoholic group. So catalytic reduction of butanol gives normal butyl alcohol, which is a primary alcohol. So the correct option is D for this question. Correct option is D. Now coming to question number 4. Question number 4, a reaction which actually requires some amount of thinking. Okay. What is the question? Which of the following options will not produce P? Now can you produce P starting from A by reaction with the dilute sulfuric acid? Can you get P starting with B by reaction with sulfuric acid? Can you get P starting with C by reaction with the dilute sulfuric acid? Can you get P starting with D on reaction with the dilute sulfuric acid? That's the question. So which are the compounds A, B, C, D on reaction with the dilute sulfuric acid will produce the compound P is the question. So we have to patiently look at each example and see whether it will give P on reaction with the dilute sulfuric acid. Okay, compound A is an alkene, and reaction with the dilute sulfuric acid means acid catalyzed hydration. So what will happen when this compound is subjected to acid catalyzed hydration? Acid catalyzed hydration. This is the compound. So a proton is added. A reaction with a proton, the proton will be added at this point, so that a positive charge will be generated at this point. Okay, so you have the product with a positive charge here, a carbocation. Carbocation chemistry is very important. There are so many reactions in organic chemistry where you come across a carbocation. And the unique property of carbocation we have already seen in the previous class, that it has the tendency to undergo rearrangement by a 1,2 hydride shift or a 1,2 methyl shift, provided the product of rearrangement is a more stable carbocation. And the dictum is a primary carbocation can rearrange into more stable secondary carbocation, and a secondary carbocation or a primary carbocation can rearrange into a more stable tertiary carbocation if the conditions are quite suitable. So in this case, this is the carbocation, and remember that there is a hydrogen atom at this point, and this hydrogen atom can be shifted to this position by a 1,2 hydride shift. That is what you call 1,2 means from adjacent position. 1,2 hydride shift means the hydrogen along with the bonding electrons, the hydrogen is shifted to this point along with the bonding electrons, and therefore what you get is this product. The positive charge is now here, and this is obviously a tertiary carbocation, and therefore this can easily react with water, and at this point an OH group will be substituted, which is same as the compound P. That means the compound A will give P as the major product. A will give P. This is A, and it gives P as the major product. So the first option actually gives the compound P. Now coming to the second option. Coming to the second option. What about this option? Will it give P as a product on reaction with the dilute sulfuric acid? It will take some time. Okay. On reaction with the dilute sulfuric acid, it is again acid catalyzed reaction. Sulfuric acid provides the proton. So at this point, proton will be there. There is no double bond here. So the site of the reaction is OH group, at which there is protonation, followed by the elimination of this water molecule. The water molecule is lost, generating a carbocation, again generating a carbocation. At this point, generating a carbocation, a secondary carbocation, and obviously this hydrogen atom here at this point can again be shifted to this positive charge here. That is a 1,2 hydride shift as in the previous example, and you will be getting a more stable carbocation with a positive charge here. And this, on reaction with the water, as in the previous case, will generate the compound P. So B also gives P as the product. B also gives P as a product. Okay. Now what about C? Can C give? Can C give? This is C. Okay. I am writing the entire thing for the benefit of all those who are attending. Some students may be finding it very easy to pick out the correct answer, to pick the correct answer. But however, we are going into the details of the options given. That's why I write the entire thing. So this compound, again a double bonded compound, on reaction with the proton in the presence of acid, the H plus will be added to the double bond, and therefore you have this carbocation. Again, this is the carbocation that you get. The H plus is added here according to Markovnikov's rule, and the positive charge is now here. And as in the previous case, the hydrogen can migrate to this positive charge here, a 1,2 hydride shift, 1,2 hydride shift, to give a carbocation which is more stable, a carbocation which is more stable, and this on reaction with the water can give P as the product. So the interesting thing is that A, B and C, even though they are different compounds, because of this unique property of rearrangement of the intermediate carbocation, all of them will give P as the product in this reaction. Now what about the compound D? What about D? Can D give, can D give product P? That's the question. Okay. So here is the double bond. Here is the double bond means Here is the double bond. Okay. So here is the double bond means the proton will be added at this double bond. The proton will be added at this double bond, and suppose the proton is added here. Actually, what you get is, okay, this is a secondary carbocation, and even if a hydrogen from here is migrating to this position, the positive charge will go only here, it will never reach here. That means the carbocation leading to the formation of P cannot be attained from this compound. If the H plus is added here, this is the product. If the H plus is added here, the positive charge will be here only, and it is very difficult for this positive charge to reach here because it will require successive hydride shifts. That generally doesn't happen. Hydride shift, just one hydride shift from the adjacent carbon can happen, and therefore you are not going to get a carbocation with a positive charge here, so that P will be the product. So the compound which does not produce P on reaction with the dilute sulfuric acid is the option D. Option D cannot give the product P on reaction with dilute sulfuric acid. I hope you understand the point. So it's carbocation chemistry, and remember that carbocation chemistry comes in the case of many a reaction, in a many a conversion. Remember the involvement of carbocation, and remember that when a carbocation chemistry is involved, don't forget that the carbocation has a unique property of rearrangement to a more stable carbocation. A primary can rearrange into a secondary then to a tertiary if the conditions are okay. Such things can happen either by a 1,2 hydride shift or a 1,2 methyl shift. 1,2 methyl shift, a methyl group with the bonding electrons will be shifted, or a hydrogen atom with the bonding electrons will be shifted to the adjacent carbon atom, and that is what is referred to as the 1,2 hydride shift, 1,2 hydride shift or 1,2 methyl shift. In these cases, we have discussed it is a hydride shift to give more stable carbocation, where you have a positive charge at this carbon, and therefore on reaction with the water, the OH group will come here and you will get this product. In all the three cases ABC, but in the case of D, we are not going to get a carbocation with a positive charge here, and therefore we are not going to get the product P. Okay. Now come to this question, question number 5. Remember that in organic chemistry in JEE Main, you often get questions of this type where there are 1 or 2 or 3 reactions connected as a sequence of reactions. One-step reactions may be rare. Of course, there may be some questions where one-step reactions are given, but in many cases, you find reactions connected one by one, maybe a 3-step reaction or a 2-step reaction, or 2 reactions connected or 3 reactions connected, like that. So it is very important that you know the chemistry of the reactions that you have studied in the various chapters. Okay, that's very important. By looking at the reagent in a particular reaction, you must be able to recall what this particular reaction is. For example, in this case is chloroform alkali. Chloroform alkali, and the substrate is a phenolic compound. Only thing is that it's a dihydric phenol, and this dihydric phenol is what you call catechol. Of course, the name is not important here. What is the structure of the product is a question. So anyway, it is catechol. That's why I told you that the name of the compound is catechol. Catechol is benzene 1,2-diol. 1,2-diol. It's 1,2-diol. That is catechol. It's a phenol. So this phenol on reaction with the chloroform and alkali. So when you read this reaction of a phenol with the chloroform and alkali, you must have in your mind the very famous reaction, what is called the Riemann-Tiemann reaction. Chloroform and alkali with a phenol. The reaction is Riemann-Tiemann reaction. Riemann-Tiemann reaction. Okay, it is Riemann-Tiemann reaction. And what is the net result of this Riemann-Tiemann reaction? Remer-Tiemann reaction is very unique. The mechanism is very unique because the chloroform alkali combination, the chloroform alkali will generate from this a very special electrophile, what you call the Dichloro Carbene. The CHCl3 will be losing an HCl on reaction with OH minus, and from it is generated the special electrophile, I must say, CCl2, and that is known as Dichloro Carbene. And the Dichloro Carbene is actually the reagent attacking the benzene ring, in this case the para position of the OH group. Of course, one of the OH group para position, the other OH group it will be meta position, but OH group, as you know, is predominantly ortho-para orienting, and here the reaction at ortho position is unlikely because there are two OH groups already at ortho positions. So the third group also going to an ortho position of the OH adjacent positions, the chances are practically nil, and therefore the CCl2 will attack preferably at the para position, and the product that is generated as a final product in the reaction is the aldehyde group here. It is the aldehyde group. So this reaction, Remer-Tiemann reaction, is something very important. You must remember this reaction. It's very important. Okay, it's a reaction of a phenol with chloroform and alkali. And on reaction with the chloroform and alkali, the attacking species is Dichloro Carbene. Dichloro Carbene is the electrophile, and the Dichloro Carbene is attacking the para position of the OH group, and at the para position of the OH group or at the ortho position, in this case the para position, because para position is more roomier and it's convenient for the electrophile to attack the para position in this case, and at the para position of the OH group you have an aldehyde group generated. Of course, the intermediate will be that CHCl2, it will be like this, CHCl2, and you can still formulate like this. The chlorine atoms are replaced by OH, the simple chemistry, and water molecule is eliminated, generating the aldehyde group. This is the simplest way in which this reaction is usually studied by students. So it is CHCl2, due to the attack by CCl2 at this point you have the CHCl2 group, and the CHCl2 group generates the aldehyde group, and therefore this is the product obtained, the para aldehyde corresponding to the catechol. That is the product A in the first step. So remember, it is Remer-Tiemann reaction. You must remember that it is Remer-Tiemann reaction, and Remer-Tiemann reaction generates an aldehyde group at the ortho or para position of the phenol, in this case at the para position of the second phenolic group, of one of the phenolic groups, I must say, of one of the phenolic groups, and the product obtained is this aldehyde. That is the compound A. This is the compound A. Now this compound, the next reaction is a reaction with methylene iodide, CH2I2, in the presence of alkali, again, in the presence of alkali. You must remember that phenolic groups are acidic. The substrate molecule as well as the product in the first step is a compound which has acidic property at the OH group. Phenols are acidic, and therefore the phenolic group can easily form the salt with alkali. So it will remain as O minus Na plus, and this will also remain as O minus Na plus. The disodium salt is formed. Phenol is acidic. Remember that. Phenol is acidic. It is not as acidic as carboxylic acid, but next to carboxylic acid in organic compounds, phenols are acidic. You might have studied that property of phenol. And why is phenol acidic? Due to the resonance in the phenol, and also due to the resonance stabilization of the phenoxide ion. You might have studied that. We are not going to those details now. Let us now try to predict what would be the product of the second reaction. So once the disodium salt is formed like this, then the methylene iodide can react here, CH2I, CH2I, and here you have NaI, and here also you have NaI. The reaction is very similar to the reaction of a phenoxide. This is phenoxide, a phenoxide with an alkyl halide. Phenoxide with an alkyl halide. The reaction is with phenoxide with an alkyl halide. That's the reaction. Okay, phenoxide with an alkyl halide, and that is which reaction? Phenoxide with alkyl halide, alkoxide with alkyl halide, and phenoxide with alkyl halide. You are reminded of the Williamson synthesis. Williamson synthesis, which is simply written as RONA plus RX. You have ROR, either, and that is Williamson synthesis. It's one of the important methods by means of which ethers are synthesized. Reaction of an alkoxide with an alkyl halide. Or to get ethers containing phenyl group, it's the reaction of a phenoxide with alkyl halide. In this case, the alkyl halide is methylene iodide. There are 2 iodine atoms, and on this part you have the 2 phenoxides groups, ONA minus here and ONA minus here. So there is a ideal situation here where this iodine can combine with this Na, or this iodine can combine with that. Means the O minus here, the phenoxide group is replacing the iodine atom of the methylene iodide this way, and also the phenoxide group at this part of the molecule replacing the iodine atom, and therefore the product obtained in the reaction is O. Okay, here you have O, and the aldehyde group remains intact. It doesn't take part in this part of the reaction. Of course, it doesn't take part in this part of the reaction, and therefore, okay, the final product obtained in the reaction is the product D. D is the final product. So here 2 important reactions are actually combined to give a very interesting question. One is the Riemann-Tiemann reaction. So you must have in your mind what is Riemann-Tiemann reaction. When you see chloroform and alkali and the substrate phenol, you must be able to recall that reaction, Riemann-Tiemann reaction. Introduction of an aldehyde group at the para position or ortho position of the OH group. In this case, at the para position of one of the OH groups, and therefore you get aldehyde. And in the second step, it's a reaction with the methylene iodide in the presence of alkali. In the presence of alkali, the 2 phenolic groups will form the disodium salt, the phenoxide, disodium phenoxide of that particular compound, and this disodium phenoxide, okay, reacts with the methylene iodide. There are 2 iodine atoms corresponding to the 2 phenoxide groups here, and the product obtained is a ether, in this case an ether of this type, and that's a typical example of Williamson synthesis. And from the mechanistic point of view, remember that the Williamson synthesis is basically a nucleophilic substitution reaction, where the nucleophile is, in this case, the phenoxide. The phenoxide is a nucleophile, and the nucleophile is attacking the carbon, holding the halogen atoms and displacing the halogen atoms. So it is phenoxide coming and the halogen is getting displaced. So the reaction is Williamson synthesis. Mechanistically, it is a Sn reaction, nucleophilic substitution reaction. So 2 important reactions combined to give a very interesting question, as I told you, the Riemann-Tiemann reaction and Williamson synthesis. Now coming to the next question, it's 2-chloro, 2-methyl pentane, 2-chloro, 2-chloro, 2-methyl pentane. This is a compound, 2-chloro, 2-methyl pentane. You can write the hydrogen atoms. So this is a compound, 2-chloro, 2-methyl pentane, and it reacts with sodium methoxide. Reaction is with the sodium methoxide, CH3O minus Na plus sodium methoxide. Again, it is a nucleophilic substitution reaction. It is a tertiary alkyl halide. Remember, this is a tertiary alkyl halide. And when a tertiary alkyl halide reacts with a nucleophile, a simple nucleophile like a methoxide ion, there are various possibilities you must remember. Of course, it's a reaction very similar to the Williamson synthesis in the previous case, reaction of an alkyl halide with a sodium alkoxide. So immediately it comes into your mind, it is probably a Williamson synthesis. But there are something more details to be understood about this reaction, because the compound is a tertiary alkyl halide, and the tertiary alkyl halide in an Sn reaction normally proceeds by an Sn1 pathway. So it is an Sn1 pathway, means what is formed in the mechanism is CH3, CH2, CH2, CCH3, CH3 positive. What is formed is a carbocation. That is the rate determining step in an Sn1 reaction. In an Sn1 reaction, the rate determining step is the generation of the carbocation by the heterolysis of the carbon-halogen bond. So that's very important. Normally it takes place in the case of tertiary alkyls, and suppose the conditions are favorable, it takes place in the case of certain secondary alkyl halides too. So here it is a well-defined case of tertiary alkyl halide, and this tertiary alkyl halide undergoes a cleavage at the carbon-carbon-chlorine bond, the carbon-chlorine bond, so as to generate a carbocation, and that is Sn1 pathway. So that's the rate determining step of an Sn1 reaction, you must know. So once this carbocation is formed, what all possibilities do exist? That's the point. The question is, which gives what all products? The question doesn't focus on the major product. You have to understand the question very clearly. The question is, yields what all products? In the choice, it is A and B, and B, all of this, C, A and C, and D, C only. Let us see what is the correct option. So in this case, this carbocation is formed. I told you, this is a carbocation that is formed. And suppose this carbocation undergoes a reaction with the OCH3 minus without any change to the carbocation. Suppose it directly combines with the CH3O minus to give a product. Then the product will be A. So there is a chance that A is a product in the reaction. There is a chance that A is a product in the reaction, because this carbocation can react with CH3O minus. It can react with the OCH3 minus to form the product A. A is a product, right? A is a product. Now what can happen? As I said earlier, the carbocation chemistry is very, very important. So here the carbocation, a tertiary carbocation, in addition to an Sn1 reaction, a tertiary carbocation is always likely to undergo an elimination reaction. You might have studied in connection with the study of Sn reactions. There is always competition between Sn reactions and elimination reactions. And this happens very often in the case of tertiary alkyl halides. Tertiary alkyl halides undergoes a Sn1 reaction, substitution by Sn1 pathway, generation of carbocation, and then the substitution by the nucleophile, okay, giving the product A, as we said. At the same time, the carbocation can undergo elimination reaction by expulsion of a proton. So when this carbocation emits a proton, this particular carbocation emits a proton forming a double bond. It can be, I once again write, CH3, CH2, CH2, CH3, CH3. This is the carbocation. So it can undergo elimination reaction, means it can emit a proton. It can expel a proton. From where can it expel a proton? It can expel a proton either from here, generating a double bond here, or it can emit a proton from here, generating a double bond here. So there is the possibility of product B. This is the product B, and there is the possibility of the product C. And suppose the question were about the major product of the reaction, it would have been the product C. The product C corresponding to the Say-Stuff rule, you know, where the double bond is attached to maximum number of alkyl groups, CH double bond C. The product C is C2H5, CH double bond C. So you have 3 plus 3, 6 plus 1, 7 hyperconjugative hydrogen atoms stabilizing the double bond. And in this case, you have only 3 plus 2 plus again here you have 3, okay, you have only 3 and 2, 5 hydrogen atoms. 5 hydrogen atoms, hyperconjugative hydrogen atoms stabilize in the double bond. So obviously the compound C is more stable than B, and therefore the major product of the reaction will be C. But here the question is not about the major product. Suppose the same question were asked as what is the major product of the reaction, then this would have been the product. Okay, but in this case, what are the possible products in the reaction? That's the question, and we find one possible product is A by the Sn1 reaction, and then carbocation, okay, eliminating a proton either from this carbon or from this carbon. A proton from here which generate a double bond here, a proton from here which generate a double bond here. So you have B and C as the products, of which C is the sized up product, and that is likely to be the product formed in major amounts. Okay, so these products are also formed, and therefore all the 3 products are possible with C as the major product in this reaction. So the correct answer to this question would be B. All of these products are possible in this reaction. So again, a wonderful carbocation chemistry. It is Sn1 reaction. Remember that in Sn1 reaction there is carbocation generation. So the carbocation can combine with a nucleophile, that is one possibility, or the carbocation can undergo, if rearrangement is possible, it will undergo rearrangement. Here already it is a tertiary carbocation, so there is no question of any rearrangement, and therefore it undergoes the elimination reaction. And there again you have 2 options. You have sized up product, and this is usually called as a Hoffman product, less likely product in this reaction. The double bond in this case is better stabilized than the double bond here by hyperconjugation, and therefore this is the sized up product of the reaction, that is a major product of the reaction. So there is a lot of chemistry to be studied about. Remember that when you study just one question, remember that there are so many details connected with the question, and you have to understand all the details connected with the question. That is how you have to study. It is not just finding the answer to the question. The discussion is not just for that, not just to pick up the answer, but to understand what are the details of chemistry involved in the entire reaction. That's why I have explained all these points. Now question number 7. You have question number 7. That's comparatively simple question. I think all of you will be able to answer this question. Only thing is that you have to look at the molecule very closely. You have to be very serious in looking at the molecule. Now, which are the reaction sites on reaction with HI? The question is, how many moles of HI are required to react with 1 mole of the given compound? The compound reacts with HI, that's the question. It reacts with HI. The question is, how many moles of HI are used in the reaction? How many moles of HI are used in the reaction? That's the question. So you have to identify the sites at which the HI can react. Of course, there is a double bond. The HI can be added to the double bond. That is one site, and 1 molecule HI will be added there. And there is an OCS3 group, the ether linkage. And ether linkage means the ether linkage is cleaved by hydroiodic acid like this. Hydroiodic acid is one of the best reagents used for causing the split of the ether linkage. And during the split of the ether linkage, in this case, here it is a benzene ring, so that this carbon-oxygen bond is stronger bond due to resonance, and therefore the bond cleaved will be the OCS3 bond like this with HI, so that H will go to O and the I will go to CH3. That is the sort of cleavage. So anyway, 1 molecule of HI is used at this site too. So at this site you have 1 molecule of HI used. At this site you have 1 molecule of HI used. And what about OH group here? It's a free OH group. Of course, it is not connected with any aromatic ring system. It's an aliphatic group here. The OH group is there, and the OH group can react with a molecule of HI, and the OH is replaced by I. It becomes CH2, CH2I. So at this site also 1 HI can react. That's a known reaction. a compound containing OH group reacts with HI forming, it's again a substitution reaction. The OH is replaced by I, a routine reaction that is possible with a compound containing an OH group on an aliphatic carbon. But remember, the OH group on an aromatic carbon, there that reaction will not work, because the OH group on aromatic carbon means the carbon-oxygen bond is stronger due to resonance. The carbon bond is stronger due to resonance. You know that? The carbon bond is stronger due to resonance, and therefore the aromatic ring oxygen bond here is stronger bond, and therefore the replacement of the OH by iodine does not take place. Do you follow? So at this point HI cannot react, at this point HI reacts, at this point HI reacts, and at the double bond also HI reacts. That means per molecule of the compound 3 molecules of HI are required, or per mole of the compound 3 moles of HI will be used. So the correct answer to the question is C. It's a very simple question. Only thing is that you have to look the molecule very carefully and identify the sites at which the HI will react, and also take care to see that the phenolic OH is not reacted upon by HI. The phenolic OH is very stable, it is not reacted upon by HI, it is not replaced by I, whereas a normal hydroxyl group in an alcohol is replaced by I on reaction with HI. So that's the chemistry that you have to remember in answering this question. Yes, coming to question number 8. So look at the molecule. Of course, it's a phenol type structure here that is attached to a aliphatic system containing a double bond far away from the aromatic ring. It has no connection with the aromatic ring. That means this part of the molecule will act as an aliphatic group. And what's the reaction that we most likely to take place when you treat this compound with an acid? When you treat the compound with an acid, the H plus will be added to the double bond. As an acid catalyzed hydration, for example, here it is treatment with an acid. Acid means it provides H plus. So H plus is the electrophile, and the electrophile is attacking the double bond. That's a routine reaction. To a double bond, H plus is added. And the H plus is added again, in this case, according to the Markovnikov's rule, very easy to understand. And what is formed therefore is, let me write like this, OH, and here you have, okay, H plus is added here, and you have the positive charge here. A carbocation, again it's carbocation that is formed as the intermediate. Addition of H plus to the double bond generates a carbocation like this. And as far as this molecule is concerned, here is a positive charge here, right? And the oxygen is here, an atom here with the lone pairs of electrons on it. So there is an ideal situation in the molecule where this lone pair of electron, it is actually something like a Lewis base, and the positive charge here, this point will act something like a Lewis acid, or simply a positive charge, and this oxygen has lone pairs. So why can't the lone pair be used to form a bond between the oxygen and this positive charge? So that is possible, thereby generating a ring at this part of the molecule. What sort of ring? 1, 2, 3, 4, 5, and an oxygen. It's a 6-membered ring. And ring formation with the 6 members or 5 members, 5-membered rings or 6-membered rings are quite likely in such reactions. Remember that. If there is a possibility of cyclization, then very often in these reactions cyclization will take place. So here is an ideal situation for cyclization. Here you have a positive charge here on this carbon, and here you have lone pairs of electrons on the oxygen atom here, and by combining them you can generate a 6-membered ring like this. A 6-membered ring is possible. The methyl group here and hydrogen here. Do you follow? So this sort of a ring closure is possible. This sort of a ring closure is possible. And finally, this molecule will again delete NH plus from it. It will expel NH plus from it, and the product obtained would be, what is the product? The product obtained will be the product given in the question as D. D is the product. D is the product given. In B, the methyl group is not seen. Okay. And the oxygen is also not seen. In B, the methyl group is there, there is no oxygen seen. In C, the oxygen is seen, but the methyl group has not seen. So which means, even by looking at the structures, you can make an intelligent guessing that the product of the reaction is this. But suppose you go into the details, you get into the details. This is how you have to understand. It is pretty easy. The H plus is added here. You have the carbocation, and this carbocation, the positive charged species, can link to the OH with the lone pairs of electrons here, thereby forming a cycle or ring, and a ring compound which is pretty stable. Ring compound is formed, and therefore the choice is D. Such things happen in certain reactions. Remember that cyclization sort of reactions will happen. Even though it's a single step reaction, you must think of the possibility of this cyclization. Even in this single step, after adding proton, you can have the cyclization here, so that the product obtained is D. And you can, as I said, by guessing, by making an intelligent guess, you can actually give the answer as D, because D is the only structure in which the methyl group is there and the oxygen atom is there. In A, there is no oxygen atom, there is no methyl group. In B, you have only a methyl group, no oxygen atom. In C, you have only the oxygen atom, no methyl group. And therefore, D is the only structure where you have a methyl group and an oxygen atom, so that D is the most probable answer, and that has been explained by this reaction. It is pretty simple. Addition of proton to the double bond followed by cyclization. Okay. Now coming to the next question. Yeah. It is 2-bromo, 2-methyl pentane. 2-bromo, 2-methyl pentane. 2-bromo, 2-methyl pentane. 2-bromo, 2-methyl pentane. And the reaction is with ethoxide ion. As we said earlier, it is already a tertiary alkyl halide. In tertiary alkyl halide undergoes substitution by Sn1 pathway, and tertiary alkyl halide is more likely to undergo elimination reaction, and the major product of the reaction is the say-stuff product. So in this case, the question is about the major product. So the major product of the reaction is the say-stuff product by elimination. And what is the say-stuff product by elimination? It is CH3, CH2, CH2. Okay, CH, okay, double bond C, CH3, CH3. We just explained the entire chemistry of it in the previous question, or the question previous to the previous question. The possible reactions we have encountered, where you have the Sn1 reaction. Along with the Sn1 reaction, there is the formation of the alkenes because of the carbocation, tertiary carbocation. There is always elimination along with the substitution in the case of Sn1 reactions. So the major product in the reactions, this is the major product of the reaction, that is A. Okay? And now this compound is subjected to the reaction what is called hydroboration. This is hydroboration oxidation. There are two parts of the reaction. One is the reaction with the BH3 diborane or B2H6, that is the usual way in which boron hydride, it doesn't exist as BH3, it exists as B2H6. But even when somebody writes BH3, it doesn't matter. It is diborane, B2H6 what is meant. And additional diborane is hydroboration and oxidation by hydrogen peroxide in the presence of alkali is oxidation. The two reactions together is what is called hydroboration oxidation. And I told you that the stereochemistry of hydroboration oxidation is anti-Markovnik of hydration. Anti-Markovnik of hydration means in the Markovnikov rule, the hydrogen is added here and the OH is added here. That is the Markovnikov rule, that the hydrogen is going to that carbon atom which already has more hydrogen atoms. But here it is anti-Markovnikov hydration. That is exactly opposite to the Markovnikov rule. That means the hydrogen is added here and the OH group is added here. That is the selectivity of this particular reaction. It is essentially anti-Markovnikov addition. The hydrogen is added to that carbon atom which has less number of hydrogen atoms, and the OH is added to that carbon atom which has more hydrogen atoms. That is just opposite to the Markovnikov rule, just contrary to the Markovnikov rule. So that's why it is called anti-Markovnikov hydration. Remember that it is anti-Markovnikov hydration to double bond, and that's why we call this particular reaction, I told you earlier, it is both regioselective and stereoselective. The stereoselectivity is this, that is a cis addition. A cis addition of H and OH, cis addition of H and OH at a double bond in an anti-Markovnikov fashion. So the product obtained is one in which the CH has OH group and the C has hydrogen atom. That means the product obtained in the reaction is D. D is the product of the reaction. This is the product of the reaction. It's a very simple conversion. Again, two reactions combined. One is the Sn1 elimination reaction. The major product is the elimination product. Remember that it is decided by the say-stuff rule. We have already written the major product. And the second step of the reaction is hydroboration oxidation. And in hydroboration oxidation, it is anti-Markovnikov. I repeat, it is anti-Markovnikov hydration. And the reaction is described as regioselective and stereoselective. Why? Because the addition of water, addition of H and OH is in a cis manner. That's why it is stereochemical, it is stereoselective. But however, that stereochemistry is not that important here as far as predicting the product is concerned. The anti-Markovnikov addition itself will give you what the product is. I hope you follow the point. Remember, it is anti-Markovnikov addition, and therefore the only product obtained is B, is this compound, that is D is the option. I hope it is clear. We will take a break for the iftar, Eid iftar. Okay, and we will meet again after 20 minutes. So thank you so much for patient listening. Welcome back. Now it is question number 10. What will be the products when carbolic acid is treated with acetic anhydride and 2 acetic anhydride in the presence of aluminum chloride? It is anhydrous, that H is missing there. It is ANHY, anhydrous AlCl3. So there is the term carbolic acid. I think all of you may be knowing that carbolic acid is another name for phenol. Carbolic acid is phenol. So instead of phenol, they have given the name carbolic acid. So one has to be familiar with that. So phenol is treated with acetic anhydride. Acetic anhydride is this compound. This is acetic anhydride, and treated with acetic anhydride, just with acetic anhydride, that is one option. And the second reaction is acetic anhydride in the presence of AlCl3. So what's the difference? That's the point. How does phenol react with acetic anhydride? Now what is the reaction site in phenol in the reaction with acetic anhydride? I hope you may be knowing a reaction called acetylation. Acetylation is a reaction in which a hydrogen atom of a group like OH is replaced by the acetyl group, CH3CO group. This is the acetyl group. And the reagent used for this purpose is acetyl chloride or acetic anhydride. Acetyl chloride or acetic anhydride is a reagent which can be used to carry out the reaction known as acetylation. Acetylation means replacement of a hydrogen atom of the OH group by COCH3 group. So that is exactly what happens in the reaction with acetic anhydride. The phenol gives phenyl acetate. It's a direct reaction. Nothing complicated. It is a direct reaction of the phenol with acetic anhydride forming phenyl acetate. That OH becomes OCOCH3. That is phenyl acetate is the product. So the first reaction is acetylation. That is simply with acetic anhydride, it is acetylation forming phenyl acetate. But suppose you carry out the reaction with acetic anhydride in the presence of AlCl3. I think when you see AlCl3, you are reminded of the Friedel and Crafts reaction. So in the presence of AlCl3, what exactly takes place is a Friedel and Crafts acylation. Friedel-Crafts acylation. In this case, the acyl group is again the acyl group COCH3, but it is this acyl group getting attached to the benzene ring. Acylation at the benzene ring, that is what happens. Friedel and Crafts reaction is a reaction taking place in the benzene ring. It's an electrophilic substitution reaction. You know, the attacking reagent is the acyl cation CH3CO plus generated from this acetic anhydride on reaction with AlCl3. AlCl3 is a catalyst which is helpful in generating the acyl cation CH3CO plus from acetic anhydride, and it is this CH3CO plus attacking the benzene ring. Attacking the benzene ring either at the ortho position or at the para position. And here if you look at the options, nothing is given in which the para position is occupied. So naturally it is the ortho position that is given in the option. It is an ortho or para orienting group, OH group, so that the COCH3 group is attacking at the ortho position with respect to the OH group, and therefore you get this compound, that is ortho hydroxyacetophenone. What you get is a ketone. C6H5 COCH3 is acetophenone. So here you have ortho hydroxyacetophenone as a product. So Friedel and Crafts acylation is the second reaction, whereas in the first case it is simply acylation or acetylation at the OH group. That's the difference. In the absence of AlCl3, it is at the OH group. In the presence of AlCl3, it is in the benzene ring. as an electrophilic substitution reaction. So naturally, the correct option is D, that is OCOCS3, that is the first product, and the second product is COCS3 at the ortho position. So D is the correct option. So remember, even it's simply with acetic anhydride, it is acetylation of the OH group. And if it is acetic anhydride in the presence of AlCl3, the reaction is taking place in the benzene ring at the ortho para positions of the OH group. And in this case, the ortho position only, the product of the ortho position is given, no product of the para position is given. But remember, it is a reaction taking place at the ortho position as well as the para position. You will get the COCS3 group at the ortho position and at the para position. Suppose a para compound is given, you would have to take that choice also. But here, you are given only the product in which the ortho group, ortho position is occupied by COCS3. So you get this product, this is the product, and this is the product. This is the first product and this is the second product, corresponding to the option D. It's a very simple reaction, nothing complicated, very straightforward reaction. Now here is a very good question. It was, I think, asked a couple of times for JEE Advanced, this particular question. The number of resonance structures of nitrogen, of N is a product of this reaction. The product of this reaction is pretty simple. The product is, we have already said that the phenolic group, now this is the phenolic group present on an naphthalene ring. You have the phenolic group is acidic, and therefore on reaction with NaOH it remains as the salt. So this is the ion, this is the ion. So the question is, how many resonance structures are possible for this ion? Because the Na plus, it is only remaining as a salt here. So the resonance structures are for the anion of this salt. So how many resonance structures are possible is the question. And of course, the question can be very easily answered knowing that phenol, this is something you must know. For phenol or its ion, phenoxide ion, you have studied it, phenoxide ion, this is O minus. How many resonance structures are there? How many resonating structures are there for a molecule of this type? What are the possibilities? The negative charge can come here, and and you will write the structure, the negative charge here, double bond O. And then the negative charge comes here like this. You have another structure, the negative charge here. So this is 1, this is 2, this is 3. And now the negative charge here, and you have the negative charge at the other ortho position. These are the resonance structures. This is 4. And finally, you have again so any molecule of this type, whether the phenol or phenoxide ion, remember that is a resonance hybrid of 5 limiting structures. So for phenoxide ion, you have 5 limiting structures. So you have to guess how many would be the limiting structures or canonical structures or resonance structures of this ion. It is something like 2 benzene rings fused at a common side. So when you start writing the resonance structures from here, for a single benzene ring with O negative there, you have 5 resonating structures. And if the 2 rings are fused like this, if you start writing the resonance structures in exactly the same way, you will have how many resonance structures? You can make an intelligent guess. How many? It will be 2 into 5, that is 10 minus 1. There will only be 9 structures. Why 1 structure less? Because the 2 rings have been fused at a common side, so that the resonance structures will be reduced by 1 and you will have total 9 resonating structures. You can peacefully write all the resonance structures at home. You can do it as a home exercise. You can write down the resonance structures of this naphthoxide ion as we have written for phenoxide, and you will see that there are 9 resonating structures. But the question can be intelligently solved by recalling that phenoxide ion has 5 resonating structures. So the naphthoxide ion has 9 resonating structures. It's a very good question, can be very easily answered if you remember that the phenoxide ion has 5 resonating structures. The naphthoxide ion will have 9 resonating structures. Okay. Yeah. Now come to this question. Of course, there is a little description there. One has to understand the description. An aromatic compound C7H8O on reaction with the bromine water gives a white precipitate of a compound with the molecular formula given. There are 3 OH groups you find, okay, where 3 bromine atoms have been substituted in the place of 3 hydrogen atoms in the compound A. H8, here it is H5. That means 3 hydrogen atoms have been substituted by 3 bromine atoms in the compound B. Now the compound A is soluble in NaOH. That means the compound A is acidic. A is acidic. Okay. Now compound C is an isomer of A. Compound C, which is an isomer of A, also gives the same reaction and gives a white precipitate of the compound in which 3 hydrogen atoms have been replaced by bromine. So A is a compound which gives the tribromo compound. The isomer of A is C, that also gives the tribromo compound. Okay. A is acidic, it reacts with alkali, whereas the compound C is insoluble in alkali, that means C is not acidic. So A gives the derivative B and C gives the derivative D, tribromo derivatives. A is acidic and C is not acidic. These are the information given. And the molecular formula of A is given. A has the molecular formula C7H8O. It's an aromatic compound because the proportion of carbon is quite large in this case and the compound is most probably aromatic. If it is aromatic, the benzene ring is there, there remains only 1 carbon atom more. So 1 carbon atom more means you put a CH3 here. And now count the number of atoms. 6 plus 1, 7. Already 1, 2, 3, 4, 5 plus 3, 8. C7H8. And then there is 1 oxygen. That means this compound must contain an OH group. In the place of H, you have an OH group. So what is given is a phenolic compound and it is justified because A is acidic. We know phenols are acidic. So it's an acidic compound corresponding to this formula C7H8O is this compound or its isomer. There are isomers, you know. You have the paracresol and you have the metacresol. These compounds are known as cresols. Cresols. If you don't remember the name, you can solve the question because the question gives only structures. Now names are given. But however, it is good to know the names of these compounds. These compounds are phenolic compounds and contains a methyl group. And therefore, compounds are known as cresols. This is orthocresol, this is metacresol, this is paracresol. Now the question is, among these 3 cresols, of course it is given that it is acidic, that is why we stick our decision to phenolic compounds. So it is cresols. And of the 3 cresols, which is the cresol which gives a tribromo compound on reaction with the bromine water? Which cresol will give a tribromo compound? The phenolic group, as you know, is orthopara orienting. Here there is an ortho position, here is a para position, but here there is no ortho position, it's already occupied. So it cannot form a tribromo compound. Now what about this compound? It has two ortho positions, but the para position is already occupied. That means it cannot form a tribromo compound. It will give only a dibromo compound. Now what about this compound? The ortho positions here, the para positions here, and the other ortho positions here. So this compound can easily form a tribromo compound. This is the tribromo compound, the ortho position and the para positions. At both the ortho positions and the para positions, which are free here, the bromination can take place because OH group is ortho-para orienting, you know. It's a highly activating group and ortho-para directing, and therefore even with bromine water, all the three positions, namely the two ortho position and the para position, can be occupied by bromine atoms. So you will get this compound. So the compound A is the compound I already wrote earlier. The compound A is the compound metacresol. This is the compound A, and its derivative B is this compound, the tribromocresol. Tribromometacristol, the tribromo derivative of metacresol. Okay. Now, there is an isomer of A which is not acidic. Which is not acidic means it is neither this nor this. It cannot be a cresol. So, is there any other isomer which is isomeric with cresol? That's the question. Is there any other isomer? Yeah, there is an isomer where it is OCH3, where you have an ether. This ether is what you call anisole, that is methoxybenzene. Methoxybenzene has the same molecular formula, C6C7, then 5 plus 3, 8, O. C5, C7, H8O. C7, H8O is the molecular formula for this compound. So remember that for cresols you have an isomeric ether. Now that is the thing that we study when we discuss the chemistry of alcohols and phenols. Alcohols are isomeric with ethers, so also phenols are isomeric with phenyl group containing ethers. Okay, so here is an ether which is isomeric with cresol. So A is the cresol, metacresol we already established, and C is the ether isomeric with A, which is anisole. And in anisole, the OCH3 group is again a moderately activating and ortho-para directing group, and therefore the reaction can take place at the ortho positions and the para positions, and it will give this tribromo derivative. Both the positions are vacant, both the ortho positions and the para positions are vacant, and the reaction can take place at these positions, and you get 2,4,6 tribromo anisole as a product. So that's the literature in the second sentence. Compound C, which is this anisole, an isomer of A, also gives the same reaction and gives a white precipitate of the compound D. So this is the compound D, and anisole is the compound C. So A is metacresol, and B is the tribromo derivative of metacresol, and C is anisole, and D is the tribromo derivative of anisole, and therefore which is the correct option? You can look into the correct option. What is the correct option? You have metacresol, okay, and the tribromo derivative, okay, and you have OCH3 anisole, and you have the tribromo anisole. So what is the option? The option is, this is A, this is B, this is C. Okay, this is A, this is B, and of course the other options are in the next page. So the option will be A. A will be the correct option, where you have metacresol and the tribromo metacresol, and anisole and the tribromo anisole as the products. I think it is clear. There is no difficult chemistry. Only thing is that there are 4 compounds which have to be identified in answering the question. That's all. Okay, these are the other options given, but it is easy to find out which is the correct option. The correct option is A. A is the correct option we have seen. Okay. Yeah. Coming to the question number 13. Question number 13. Okay. Complete the following reaction. the question is pretty simple, but the answers, there are again 4 compounds to be identified, A, B, C, D, A, B, C, D, A, B, C, D and A, B, C, D. So, all the 4 options contain 4 compounds A, B, C, D. And the structures of these 4 compounds are comparatively, the structures A are very similar, the structures B are very similar, structures C are also very similar, structures D are also very similar. So, there is always a chance that you mark the wrong answer unless you are conscious about picking the right answer. So, you have to understand the chemistry, but the chemistry is not complicated. The chemistry is simple chemistry. It is tetrahydrofuran, and the reaction with the excess HI, reaction with excess HI. Reaction with excess HI means that the tetrahydrofuran, which is a cyclic ether, reaction with the HI, cleavage here, okay, HI, and again a cleavage here, HI. So, what is the product obtained? The product obtained is CH2, CH2I, CH2, CH2I. Simple chemistry. The ether linkage is actually split up. The ether linkage is undergoing the cleavage with the hydrodic acid. If it were with one HI, it would have been OH and I here, but with excess HI means at the other portion also the HI will react, and therefore this is the compound. So, obviously this is the compound A. No other option. This is the compound A. This is the compound A. Okay? And now you are performing a reaction on A. On this compound you are doing a reaction. What's the reaction? The reaction is with the magnesium in the presence of ether, in either medium. Not in the presence of ether, it is in either medium. Ether is a solvent for preparing a Grignard reagent. So, you react with magnesium in the solvent ether. It forms the Grignard reagent. And what is the Grignard reagent? The Grignard reagent is CH2. Okay? Anybody can write that, MgI. And here also CH2, CH2, MgI. This is a Grignard reagent. And this Grignard reagent, on reaction with carbon dioxide, that is the second step. Carbon dioxide, what will happen? The Grignard reagent will react with the carbon dioxide at both these points, and you have CH2, CH2, okay, COO, MgI, and here also CH2, CH2, COO, MgI at this part also, and it is subjected to hydrolysis, H3O positive hydrolysis. You have CH2, CH2, COOH, CH2, CH2, COOH. A very familiar reaction, no complication at all. So, that is the compound B. So, tetrahydrofuran, cleavage with excess HI, you are getting that diiodide, reaction with the Grignard reagent and magnesium to get the Grignard reagent, reacts with carbon dioxide. At both the Grignard reagent parts of this substrate, you have reaction taking place, and on hydrolysis, it gives the dicarboxylic acid. You know what it is? 1, 2, 3, 4, 5, 6. It is hexane 1,6-dioic acid, what is called the adipic acid. Anyway, the name is not important here. What is asked is the structures of the compounds. But however, it is good when you study the name of the compound too. The name of the compound is adipic acid. So, this is the compound B. Now, what are C and D? The compound A is given compound A, CH2I, this is the compound. So, this compound is subjected to the reaction with alkali. It's an alkali, it's an alkyl halide, and reaction with alkali means a simple Sn1 reaction by means of which the I will be replaced by OH. Anybody can write that. You have CH2OH and this is CH2, CH2OH. So, that is the product obtained. The iodine atoms are replaced by OH group by Sn reaction, and you get the dihydric compound CH2, CH2OH, CH2, CH2OH. And this compound is then subjected to, this is the compound C, and then subjected to oxidation by potassium permanganate. It is like a glycol, and the CH2OH group, that is the primary alcoholic group, on oxidation by acidified permanganate, the groups will be oxidized to acid group. So you get CH2COOH, and this part also it is CH2COOH. Oxidation of the primary alcoholic group to carboxyl group as a final product, and that is the product D. So it is very simple chemistry. A is this compound, the diiodo compound, and B is the dicarboxylic acid, and a carbon dioxide addition is here, a carbon dioxide reaction is here, the addition of the Grignard reagent to carbon dioxide, and remember, one carbon atom is generated here. That's why you are having a dicarboxylic acid containing 6 carbon atoms from this compound containing 4 carbon atoms. The 2 carbon atoms are due to the 2 CO2 molecules reacting at the Grignard reagent. And in the latter conversion, it is the replacement of the iodine by OH. You have the dihydric compound, what is generally called a glycol. Glycol is usually the name when it is 1,2-glycol. This is not actually 1,2-glycol, 1, 2, 3, 4. It's a 1,4-glycol, and on oxidation with potassium permanganate, the primary alcoholic groups at the terminals are getting oxidized to carboxyl groups, and therefore you get this D as the acid, and this acid, as you know, is succinic acid. This acid is adipic acid, okay, and this acid is succinic acid. So these are the options. So A is this compound CH2CH2I, CH2CH2I, and B is the compound adipic acid given by this formula, and C is the compound CH2CH2OH, CH2CH2OH, and D is the compound CH2COOH, CH2COOH. So these 4 structures, if correctly written, that is the correct option. That's the correct option. The option is given in the next page. The options are given in the next page. The options are given in the next page. So what is the correct option? You have CH2, CH2I, CH2, CH2I, that is A. And then you have CH2, CH2COOH, CH2COOH, okay, that is B. And C is the dihydroxy compound, CH2, CH2OH, CH2, CH2OH, okay. And D is the compound CH2COOH, CH2COOH. So what is the correct option? The correct option is B. B is the correct option. B is among the options. B is the correct options. Rather than just picking the option, you try to understand. You try to understand what are the products formed in the reaction and the chemistry of the reaction. It's a very simple chemistry, routine chemistry. There are no complications. There are no rearrangements. It's only simple chemistry, simple reactions involved. But you have to be very careful in choosing the structures, because when you look at the structures, many of the structures seem to be similar. So what is the right structure? You have to choose the right structure. That is the important thing. Okay. So there we take a break again for 1 or 2 minutes. Okay. Welcome back. Let us come to the next question. Question number 14. Arrange the following compounds in increasing order reactivity in an Sn2 reaction with the potassium iodide in acetone solvent. This is a reaction which is usually known after the person's name. I think in the chemistry on alkyl halides or haloalkanes, you have some name reactions of importance. The Hans-Decker reaction, the Swart reaction, and the Finkelstein reaction. And this particular question is about the Finkelstein reaction, which you may be knowing it's a reaction of an alkyl chloride or bromide. Alkyl chloride or bromide with iodide ions. You use potassium iodide or sodium iodide in a solvent like acetone or methanol. This is a solvent used. In which case, the chlorine or bromine is replaced by iodine to give an alkyl iodide. This reaction is what you call the Finkelstein reaction. It is Finkelstein reaction. So this is a Finkelstein reaction here. Sn2 reaction with the potassium iodide in acetone solvent. Potassium iodide reacts means what is the other product of the reaction will be potassium chloride or potassium bromide. And actually the driving force of this reaction you might have studied is the low solubility of these compounds in acetone. And if you compare the solubility of KCl and KBr, KCl is more soluble, KCl is less soluble. That's the point. KCl is less soluble and therefore gets easily precipitated. The byproduct KCl easily gets precipitated and then KBr gets precipitated. So the ease of precipitation, once it is precipitated, there is absolutely no chance for the backward reaction. That's the point. So KCl is precipitated means the reaction will be channelized in the forward direction. So that is actually the driving force. The solubility of the byproduct in the reaction, the inorganic byproduct in the reaction, in the solvent of the reaction, that is acetone or methanol. That's why the solvent is very important in this reaction. The solvent used is acetone or methanol, in which the chloride or bromide is not that soluble and therefore they get precipitated. If you compare the solubility, KCl is less soluble and therefore more easily gets precipitated than KBr. Do you follow? And obviously the reactivity of 2 and 3 will be more than for 1 and 2 because 2 and 3 are alkyl chlorides and 4 and 1 are alkyl bromides. So obviously 2 and 3 will be more reactive than 1 and 4. So the correct choice will be the choice in which 1 and 2 are 3 and 4 coming and 2 and 3 are towards the end of the series and 1 and 4 are at the start of the series. And even when you compare 2 and 3, of 2 and 3, 2 is simply cyclohexyl chloride, whereas this is a tertiary, which is a rather crowded molecule, sterically hindered chlorine atom. So obviously of these two compounds, 2 and 3, it will be the compound 2 which is more reactive. This is more reactive than 3, the two chloro compounds. Similarly, if you take 1 and 4, the two bromo compounds which will come next in reactivity, actually the compound 4 is less reactive than this compound. Here the bromine is on an aliphatic, purely aliphatic, which is not crowded, whereas here is a ring system. The bromine atom is on a ring system. So if these two compounds 1 and 4, again the compound 1 will be more reactive than 4. So the 4 is the least reactive, then comes 1 and then comes 3 and then comes 2. So the correct order of the increasing reactivity is 4, okay, less than 4 less than 1, less than 3, less than 2. So it's only simple chemistry. Remember that the Finkelstein reaction is based on the solubility of the inorganic byproduct in the reaction in the solvent acetone or methanol. There's KCl is less soluble and for most easily precipitated. So if the chloride, the reactivity is more than for bromide, and of 2 and 3, the reactivity is more for 2 because 3 is a crowded molecule. So the chlorine is a bit sterically hindered by the other part of the molecule. Similarly, among 1 and 4, here the bromine atom is on purely an aliphatic carbon, which is remaining as a side chain here. So it is not at all disturbed, there is no steric hindrance or anything like that there. And here it is bromine attached to a cyclohexane ring. So obviously this will be more reactive than this as far as an SN reaction is concerned or an SN2 reaction is concerned, because in SN2 reaction, you know, the transition state is the important thing and the steric hindrance is the deciding factor. So less the steric hindrance, more the reactivity, and that's why 2 is more reactive than 3, and that's why 1 is more reactive than 4. So the overall reactivity order is 4 less than 1 less than 3 less than 2. Okay, so that is a question based on Finkelstein reaction. So the theme is very simple here. There are no complicated conversions or anything of the sort, but there is a little theoretical chemistry involved, and that is the driving force of Finkelstein reaction and the stability of the transition state in reactions and so on. Okay, so coming to now question 15. Question 15 is again a question where you have to think a little bit. Okay, the second ring is also a 5-membered ring. Okay, this is the compound where you are given a bromine atom, okay, a bromine atom here. It's a 5-membered ring, and a bromine atom here, and it is heating with water. That heating is given. That's very important. A reaction where the solvent itself takes part in the reaction. A fission of the compound by solvent is what is generally called as the solvolysis. So the nucleophile here, it's an alkyl halide sort of compound, and the nucleophile here is water, which is a very weak nucleophile, you know, very weak nucleophile, and the solvent itself is a nucleophile, but there is cleavage by solvent. That's why the reaction is called solvolysis. So the solvent is a nucleophile in the reaction, and water, as you know, is a weak nucleophile, and the reaction is under heating conditions, and under these two conditions, that means weak nucleophile and heating, the reaction is most probably taking place by a carbocation intermediate. That means again you are coming to the chemistry of carbohydrates. Here you have 5 carbon atoms, here also you have 5 carbon atoms, and here you have bromine. Okay, here you have a double bond, here you have methyl. So what is the carbocation formed? At this point the carbocation is formed. Here is the carbocation. At this point you have the carbocation, and this carbocation can obviously react with water. At that position itself it can react with water, in which case the product A would be formed. There is nothing wrong in suggesting the product A, because this is a carbocation, and this carbocation simply undergoes a substitution with the nucleophile, and you have product A. So A is a possible product. Here the question is, what are the expected products? The question is not about the major product. So what are the possible products? Now questions of this type will be asked in 2 ways. What is a major product? And sometimes they will ask you to just pick the possible products in the reaction. So here the question is about the possible product. So as we said earlier, for the carbocation, it can have a simple SN reaction, and you can get A is the product in the reaction. So A is possible. Now what about the product B? Is there any chance of getting the product B? That's the question. So once this carbocation is formed, remember that it is a 5-membered ring here. And you might have seen examples earlier in classrooms while this point is being discussed. 5-membered ring always has some tendency to get expanded into a 6-membered ring. So if the carbocation chemistry, if the carbocation structural the structure is such that it can undergo a ring expansion to give a 6-membered ring. Such a thing can easily happen. So for example, at this point, suppose an expansion takes place so that the right ring will be 1, 2, 3, 4, 5, 6. It will be a 5-membered ring, okay, connecting which you have a 6-membered ring. Right? Okay. So that's the carbocation that you get, and this carbocation will have a positive charge here. You can have the positive charge here, it can expand. You can have the positive charge here, it's a double bond methyl group. That means you can have the positive charge here, the positive charge here, or you can have a structure in which, okay, you have the positive charge here with the double bond here in the middle. So that is possible. It is possible. It is from here. This bond is actually the bond broken, and when these electrons are utilized in forming a bond here at these two ends, remember the electron is lost from this carbon. That's why the positive charge is on this product from this structure or the product from this structure on reaction with a water molecule. And if this reacts with the water molecule, you get the product A. And if this reacts with the water molecule, if this reacts with the water molecule, you are getting the product. This is the product. I mean, if you are reacting, water molecule is reacting here, you are getting this product. And if the water molecule is reacting in the other way with the other carbocation, you are getting this. So you have A, B and D as the possible product, and this product will not be obtained. If you carefully look at it, if neither this nor this can lead to this product will not be obtained. Of course, at the positive charge it can be OH group, but the double bond CH3 is here only, it is not here double bond CH3. So there is no possibility of the product C in this reaction, because these are the only 3 carbocations you have, and these 3 products A, B and D are the products from these 3 carbocations, the original carbocation and the rearranged carbocations, and this product is not formed in the reaction. So the Solvolysis products are A, B and D. A, B and D. You have all the 3 products A, B and D in Solvolysis. A good question, because one has to know about the possibility of the rearrangement by ring expansion. So that is possible in the case of carbocations. In certain reactions you have ring expansions. A 5-membered ring can become a 6-membered ring, or a 4-membered ring can become a 5-membered ring. So like that, ring expansion possibilities are there. But you must also have in mind that there are certain situations where a ring contraction possibility is also there in the rearrangement of carbocation. Perhaps we may come across such a case in the following discussions. Now this question 16. So look at the question, it's very simple. I think we can finish it within a couple of minutes. So this question, it is again a phenolic compound. Of course, a methoxy group is there at this point at the meta position of the phenolic group. And the reactions with this compound CH2Cl, CH2COCl. And that the COCl means it's an acyl chloride. It's an acyl chloride. Acyl chloride, and you have anhydrous AlCl3. Acyl chloride and anhydrous AlCl3 means the most probable reaction is Friedel-Crafts acylation. So where will the Friedel-Crafts acylation take place? The OH group is ortho-para orienting, so this is the ortho position and this is the para position. The methoxy group is again ortho-para orienting. So it is its para position and this is its ortho position. So there are 2 positions where the 2 effects of the 2 groups actually reinforce. One is at this point and the other is at this point, and the third is at this point, ortho with respect to OH and ortho with. But here the reaction is very unlikely because the two groups are there on adjacent sides. So in fact, the Romier position is this, and moreover, it is with regard to the OH group at the ortho position. So the reaction can most likely take place at this position, so that the product of the reaction is OCH3, you have OH, and it is this group that is getting substituted. You have a Cu group, okay, then you have CH2, and then you have CH2, and then you have Cl, okay. So once you find the molecule in this configuration, in this geometry, we are also reminded of the possibility of cyclization. So that is exactly what happens. A cyclization, after the Friedel and Krauss reaction, you have a cyclization of where the HCl is eliminated, and therefore the product obtained in the reaction is OCH3, okay, CO, CH2, CH2. So that's the product in the reaction. So it is Friedel-Krauss reaction, Friedel-Krauss acylation, because this compound is an acyl chloride, the Friedel-Krauss acylation at this point, followed by cyclization, and this is the product, and this is the product that is given by a structure. What is the structure? This is the product given by structure C. C is the structure. It is CO, CH2, CH2, CO, CH2, CH2, and here is an oxygen. So C is the correct option for this reaction. At least some of you may be thinking that why this reaction specifically at the OCOCl group, why can't you have a Friedel-Krauss alkylation at this part of the molecule? If it is a Friedel-Krauss alkylation at this part of the molecule, then even if you think of such a possibility, the OH group here, and then you can have the alkylation here, COCl, okay. Then alkylation here means at this part, why can't you have an HCl elimination? So that here you have OCOCH, CH2. And this will undergo a rearrangement in which this group will be migrating to this position, and there again we get this as the final product. Moreover, you have to understand that when we have a molecule like this, the more reactive part of the molecule is the acid chloride part. The acid chloride part is the most reactive, and therefore the reaction is likely to take place in the former pathway leading to this product. And even if a student thinks the latter possibility, then the latter possibility will give this compound. So there again NHO, HCl sort of elimination that will happen, and but a rearrangement will take place so that the compound will go to this structure. So this is not the possibility, this is the right possibility, and you have C as the major. Remember that the acyl chloride part of the molecule is more reactive than the alkyl part, and what is taking place is a Friedel-Krauss acylation with the acyl chloride here rather than a Friedel-Krauss alkylation with the alkyl chloride part of the molecule here. And that is how you have to rationalize the pathway of the reaction. Okay. And now here is again a slightly difficult question for you. What are the possible dehydration products? What is the product is not the question, or what is the major product is not the question, and what are the possible dehydration products in the following reaction? There are 4 products given. So what are the possible products in this reaction? That's the question. What are the possible products in the reaction? That's the question. So what all possible products are there for this molecule? That is what you have to understand. Okay, so here again, in the presence of sulfuric acid means there is a formation of, now even the questions are totally different. Many of the questions involve the theme of carbocation formation and the rearrangement of carbocation, that's there. So this is the initial thing that is formed in the reaction. And it is obvious that a H2O molecule can be removed here, a double bond may be here, and obviously when the pi electrons are shifted to this position, you can have a pi bond here, and when a proton is lost from this position, you can have two double bonds. That means from this you can get compound, this one, one compound, you have this compound, and you have the other compound. That means this compound is possible, and you can also have this compound. These two compounds are possible. These two compounds are possible starting with this carbocation, because a proton is lost means a double bond will be created, and from this position again a double bond is created. That means OH is again protonated and water molecule is lost. You will have a double bond here, and you can have double bond here, the conjugated double bonds, here also conjugated double bonds. So these substrate can give rise to these two products again by proton elimination. So these two products are possible. That is, product C and D are possible from this carbocation. And now the intriguing question is whether A is possible or B is possible. So there one has to think a little bit, whether B is possible, whether A is possible. Okay, B will be possible. B will be possible if remember, if these electrons from here actually form from here, form a bond here, a shift of this bond to this position, to the positive charge, something like a carbocation rearrangement, in which the second ring formed is 1, 2, 3, 4, 5, a 5-membered ring. I told you that there is also some possibility of this type of ring contraction, but there is only to a small extent. Remember that these are the major products. Suppose the question is about the major products, these are obviously the major products. But being a carbocation, it can also undergo a rearrangement like this. And if this sort of a rearrangement happens, it will be a 6-membered ring, and here you have a 5-membered ring, and here you have an OH group from which a proton may be removed, and you may get this product. So there is a chance for this product, at least in small amounts, this sort of a product may also be formed. That means B is also a possible dehydration product. We don't know the percentage. It may be only 5%, it may be only 10%, and these two compounds may be 40% and 40%. So C and D are formed in larger proportions and B is formed in smaller proportion. Such a possibility also exists. A ring contraction in certain cases, a ring contraction is also possible when we discuss carbocation rearrangement. What is more likely is ring expansion. As I told you earlier, 6-membered ring systems or 5-membered ring systems which are thermodynamically more stable than other systems. So such systems may be possible, but there may be the possibility that in compound of this type, a ring contraction may take place at one of the rings so that you can have a product like B. Product C and D are formed from this structure I told you, and from the rearranged structure, the carbocation rearrangement, you can have the product B, and there is absolutely no chance of getting the product A. By any of these mechanisms, you are not able to get A, and therefore the correct answer for these are B, C and D. It's a multiple answer type questions usually appears in advanced paper, but even in the JEE main paper, this question may be asked by giving the choices like A, ACD, B, BCD, C, A and C only, D, AB only. So like that, question may be asked like that. Even this question for JEE main may be asked. It's a good question where you will have to think of this contraction possibility to have this compound. If this compound is given, obviously you can suggest a contraction of this second ring by carbocation rearrangement with the contraction of the ring and formation of this ketone as a product by expulsion of a proton. And these two products, by expulsion of protons from both the OH groups, you are having these compounds with the two double bonds which are conjugated, double bonds which are conjugated. Okay, so that's about question 17. It's a good question, good question. Now here you have an alcohol of the formula C6H12O, that is question 18, and it gives immediate turbidity. You have to listen to that. Immediate turbidity with cold concentrated HCl, even in the absence of sudden Cl2, means the compound is a tertiary alcohol. You are reminded of the Lucas test, where the reagent is concentrated hydrochloric acid and anhydrous zinc chloride, and the tertiary alcohol gives a immediate turbidity. Secondary alcohol gives turbidity after some time, and the primary alcohol gives a turbidity only very slowly or doesn't give a turbidity at all. A simple test which can be used to differentiate among the three types of alcohols, primary, secondary and tertiary. Every one of you may be knowing. Now here is that reagent used here with this particular alcohol. So our impression is that C6H12O is a tertiary alcohol. Okay, it's a tertiary alcohol. And then a little more information is given that X can also be obtained by treatment of either with excess of sodium Cl2. And it is also given, the third thing is important, X can also be obtained by treatment of an ester with excess of methyl magnesium bromide. Okay? And I have said it already in connection with my previous class, couple of days back, that the reaction of formaldehyde with the Grignard reagent gives a primary alcohol. The reaction of other aldehydes with the Grignard reagent gives a secondary alcohol. And the reaction of a ketone with the Grignard reagent gives a tertiary alcohol. And the reaction of an ester with excess of Grignard reagent, you require 2 moles of Grignard reagent. The reaction of an ester with excess of Grignard reagent also gives a tertiary alcohol. So there are two very important informations. With the Lucas reagent, you have an immediate turbidity, means it's a tertiary alcohol. And with an ester, when it reacts with a Grignard reagent, you have a tertiary alcohol. So these two informations are okay, as saying that the compound X is a tertiary alcohol. X is tertiary alcohol. But which tertiary alcohol is a question? What are the possibilities? If it is a 6 carbon containing tertiary alcohol, what are the possibilities? Okay, what are the possibilities you can have? Possibility means you can have this compound, 6 carbon atoms. You can have, not here, but here you have OH group. So this is one possibility, where you have 2 methyl groups on this carbon. Okay, or the possibility is CC, C, OH group, and here you have CH2, CH3 and CH3. That's also is a tertiary alcohol. Okay, that is the second possibility, where you have a tertiary alcohol. And the third possibility is you can have tertiary alcohol. Is there any other possibility? You can have a tertiary alcohol. For example, COH, you have CH3, CH3, and you can have CH3, CH3. That is also a tertiary alcohol. Do you follow? So these are the possibilities. This is a tertiary alcohol. This is a tertiary alcohol. This also is a tertiary alcohol. But you must go to the question, when an ester is reacted with excess of methyl magnesium bromide, and then by acid hydrolysis, you must get this particular tertiary alcohol, which means the tertiary alcohol must contain 2 methyl groups on the same carbon atom. 2 methyl groups. So this is not possible, and here this also is possible. There are 2 methyl groups on the same carbon. So you have to make a judgment between these two, which will be the compound. You are given so many options here. It is 3-methyl 3-pentanol, 3-methyl 3-pentanol, which is 3-methyl 3-pentanol, 3-methyl 3-pentanol. It doesn't contain 2 methyl groups. With excess methyl magnesium bromide, 2 moles of methyl magnesium bromide, the tertiary alcoholic group must have 2 methyl groups on the carbon atom. So that's not possible here. So 1 is not the option. 2-methyl 3-pentanol, 2-methyl 3-pentanol. Okay, 2-methyl 3-pentanol. That is also not possible because the carbon containing the OH group doesn't have 2 carbon atoms. So second option is also not correct. And what is the third option? It is 2-methyl 2-pentanol, 2-methyl 2-pentanol. It is this option, 2-methyl 2-pentanol, can be obtained by the reaction of an ester containing 3 carbon atoms with the 2 molecules of methyl magnesium bromide or methyl magnesium iodide. So this is correct, 2-methyl 2-pentanol, 2-methyl 2-pentanol. C is the correct option. So C is the correct option. It is 2-methyl 2-pentanol. So is enough clue is given as to decide which is the compound. The important thing is that at the COH group there must be 2 methyl groups because the compound is obtained by reaction with excess of methyl magnesium. So that's a clue that carbon carrying OH group, you have 2 methyl groups. So check the 3 options which contains 2 methyl groups on the carbon carrying OH group. That's the correct option, and we find that it is 2-methyl 2-pentanol. Not at all a difficult question. It's a very simple question. Okay, the major organic product. Yes, here comes the question, the major organic product. It's a phenyl group here, and this part it is cyclic, and this is an ether. Remember that it is an ether, and the ether oxygen is attached to the phenyl group. And I have already told you on many occasions that when you have an ether where the oxygen is attached to a phenyl group, this bond, the bond between oxygen and the phenyl group, this bond is pretty strong due to resonance, and the bond is not easily cleaved on reaction with HI or HBr. So the cleavage will always take place in this fashion with the hydrogen here and the bromine here. So also what happens here, on this you have the hydrogen and here you have the bromine. That is the cleavage taking place. If the cleavage is taking place, you have OH here, and then you have a bromine here. Then you have a bromine here. So the product is D. It's a one-step question, perhaps the simplest of the questions asked in this particular question paper. It is the simplest. It gives just one, it involves just one reaction, but you must know the mode of cleavage. That's very important. The oxygen carbon bond of the phenolic part of the aromatic ether part, it is not actually cleaved. The cleavage takes place on the other bond only. It is always like this. We have already seen with inosol, the cleavage of the inosol is only like this. We have seen in connection with an earlier example and also in the previous class, it seems. So the cleavage is always like this. It's an important thing that you remember. And if you look into the previous JEE main question papers, there are many question papers in which this aspect is tested. That is, you will be given an ether linkage where the ether linkage is attached to a aromatic ring, and then that linkage is not broken. It is the other linkage, the alkyl oxygen bond, that is undergoing fission, and it's not the aryl oxygen bond. The aryl oxygen bond is stronger than the alkyl oxygen bond in ethers, aromatic ethers, and therefore the cleavage takes place only like this. So here the cleavage is like this, and therefore the product 4 is the only product of this reaction. It's very simple, but you must remember this chemistry, this particular chemistry of the cleavage. Now coming to question number 20, we have only limited minutes left behind, so let us rush a little bit. Consider the following chain of reactions. This compound is subjected to a reduction by lithium aluminum hydride. You have a product which is subsequently treated with an acid, sulfuric acid and water. And what is speciality of the lithium aluminum hydride on this particular substrate? It's a compound which contains the double bond and you have the carbonyl group, right? And we have told you several times, I have told you several times that lithium aluminum hydride, though a powerful reducing agent, it can reduce an ester directly into a primary alcohol. It can reduce aldehyde into a primary alcohol. It can reduce a ketone into a secondary alcohol. Or in general, it can reduce that CO into CHOH. That's there. But however, lithium aluminum hydride will not touch the double bond. Remember that. It will not touch the double bond. Lithium aluminum hydride will not touch the double bond, and therefore the first product formed is this product, CHOH. This is CHOH. This is the first product formed. And the next reaction with the sulfuric acid, that is acid catalyzed hydration. Hydration will take place here at the double bond. Acid catalyzed hydration at the double bond. And here you have CH3, and here you have CH, OH, and then you have CH2 here, and then you have CH2 there, and then you have CH, OH, CH3. This is the compound formed. This is the compound formed in acid catalyzed hydration. This is the compound formed, and here you have H2O being eliminated. H2O eliminated means you have the compound CH3CH, CH2, CH2, CH. Okay, between them you have an OH group and methyl. So the product of the reaction is B. A simple question, but you must think of this possibility of cyclization. I think you have seen so many examples where cyclization is possible. So always have in mind the possibility of cyclization in such reactions. Of course, the groups are at the adjoint carbon atoms. 1-2 carbon atoms, no cyclization will take place. Cyclization usually giving 5-membered ring systems or 6-membered ring systems. Remember that. So here is an ideal situation where you have 2 OH groups, and between the OH groups a water molecule may be removed, and you have a cyclic ether. You are having a cyclic ether. It is a cyclic ether containing 5 carbon atoms. You have 2 methyl groups, and in between you have an oxygen atom. Cyclic ether is. So that is again very simple. Now let us come to the questions, single digit answer questions. C4H9 CH7Cl. I think in all classrooms this question is discussed, and to my students I have discussed this question several times. C4H7Cl means it's a compound containing double bond and it is a compound containing chlorine atom. So you have to think of the possibilities. Suppose to substitute the chlorine atom, here it is CH2, here it is CH, here it is CH3, here it is CH3. And if you substitute a chlorine atom here, you have a chlorine here, means this will lead to a compound like this, okay? And here you can have these 2 groups on the same side or on opposite side, and correspondingly this particular compound will have 2 geometrical isomers. You get 2 isomers here. Cis-trans isomerism is possible in a compound of this type. If you substitute a chlorine here, then again you have no cis-trans isomerism, because the compound would be CH3CH2, CCl double bond CH2 will be the compound, and here there is no chance of, and therefore there is only 1 isomer. And if you substitute the chlorine here, you have CH3, CHCl, okay, CH double bond CH2, and here this carbon becomes chiral, and therefore you have the dextro isomer and the levo isomer. You have 2 isomeric compounds. And if you substitute the chlorine here, you have ClCH2, CH2, okay, CH double bond CH2. So you have only one isomer. Okay. And now take the compound where you have the double bond like this and a carbon present as a side chain, and you put a chlorine here. If you put a chlorine here, compound is CH3, CH3, here you have CH2, and if you replace hydrogen by chlorine, you have this compound with the two methyl groups on this carbon. That means it doesn't exhibit geometrical isomer, you have only one isomer. And if you have CH3C, if this methyl group is substituted here, you have, what about this compound? CH3C, CH2Cl, double bond CH2, that is possible. However, this compound also can have only one isomer. Okay, so you can count the number of isomers, whether there is possibility of geometrical isomerism, and count. And if you do the entire business of this sort of writing the isomers, you have 5, 6, 7, 8. Then there are more isomers. I think you have more isomers. You can have more isomers, possibility of more isomers you have. If you put the compound like this, you have CH2 double bond, CH double bond, CCl, CH3. If you write this compound, such a compound is also possible. And in that case, you can have geometrical isomerism. So for this compound, you have two geometrical isomers. And if you have, again, the possibility of this sort of isomerism, C double bond C, CH2Cl, I think we have already written. You have geometrical isomerism possible in this case also. So by counting all such compounds, you will be able to see that you have as many as 12 isomeric compounds for this compound, C4H7Cl. And it will be a good exercise for you if you write down all the possible isomeric compounds and also write down the names of the isomeric compound and gets convinced that these compounds do have different names. If two compounds have the same name, it means that the compound is the same. But you will see that these compounds are different. If you systematically write down the names of these IUPAC names of these compounds, you will see the compounds are different. So you can count the geometrical isomers, you have to count the stereoisomers. That's very, very important. About the total number of isomers, whenever a question of that sort is asked, don't forget about the geometrical isomers and the optical isomers. That's why even for a compound of this type, C4H7Cl, there are two functionalities. One is a chlorine and the other is a double bond. You work out the possible options where you have the double bond and the chlorine, and allot the chlorine on the carbon atoms one by one, and then think about the possibility of geometrical isomerism or optical isomerism in this case, and then work out the total number of isomers. I tell you, this particular question has been asked even earlier, and it's a good question. It is a good exercise for you to write down all the 12 isomers. You just write down all the 12 isomers of this compound and get convinced that this has 12 isomers. Now coming to this question, consider the following. Again, a solvolysis reaction. You are giving a compound like this, and again the question is based on the Sn1 mechanism. It is specifically mentioned that how many principal products would be formed if the reaction follows Sn1 mechanism. Sn1 mechanism means the bromine is lost from here and you have a carbocation, and once this carbocation formed, what all possibilities do exist? What all possibilities exist? You have CH3C, CH3. It's a simple question because with whatever information I have already told you in connection with the previous questions today, you can answer this question with a positive charge here. That means an OH, that C2H5O, OH can attack at this position so that you can get one product. Okay, and then the carbocation here can undergo a rearrangement. This carbocation can undergo a rearrangement. Okay, if this product is there, CH3, CH3, okay, CH, you have OC2H5 in the first reaction, CH2CH3. So this is the product, but however you must remember that this carbon is chiral, and therefore this product itself is dextro and levo. You have two products, that's okay. And then you have the carbocation CCH3, CH3, okay, CH, CH2, CH3, this carbocation, and this carbocation, suppose this carbocation undergoes a rearrangement. How can it undergo a rearrangement? You can undergo a rearrangement here. Principal products by an Sn1 mechanism, because nothing is said about the elimination reaction here. You need not think about elimination because it's only Sn1 mechanism that is given. So you have to understand what are the substitution products possible when that OC2H5 substitute here you already seen. You have dextro and levo. Now this is the other possibility. The other possibility, you have the carbocation. Now suppose it undergoes a rearrangement. At this point you have a carbocation. If this carbocation is there, it is C6H5 here, doesn't matter. And suppose a rearrangement takes place. At this point a rearrangement takes place. You have what product? You have a product. Actually, the question is about, consider Solvolysis reaction. You have a product. In this case, okay, with this carbocation, if it carbocation undergoes a rearrangement that this methyl group is migrating to this position, you have C6H5 CH3, then CH3, CH2CH3, that is possibility is there. You have the possibility, and you have that OCH2H5 group coming here, and you have C6H5 CCH3 OC2H5, okay, C2H5 CH3, this is there. And in this case also you have remember this compound, that's very important, this compound. Here this carbon atom is chiral and this carbon atom is also chiral. This carbon atom is chiral and this carbon atom is chiral, means you have two chiral carbon atoms in this compound, two dissimilar chiral carbon atoms. I had told about this point even earlier in my earlier discussion. If you have two dissimilar chiral carbon atoms in a compound, you have 2 square, that is equal to 4 optical isomers. That means 2 pairs of enantiomers. 2 pairs of enantiomers. So when this compound, when this carbocation gives a rearranged carbocation, or this carbocation directly gives that product, actually, remember that you are getting 2 pairs of enantiomers, and from this you get only one compound. So altogether you will get 4 plus 1 plus 1, that means you will be getting 6 products in this reaction. So that's very important question. From this you have one substitution product here, but this is chiral, and therefore you have dextro and levo. And the carbocation, if this carbocation undergoes the rearrangement, okay, and then substitution by OC2H5 will give a product in which there are 2 chiral carbon atoms, and therefore you get 2 pairs of enantiomers. And if it gives, this carbocation directly reacts with the C2H5OH, then it gives just one product, which is dextro or levo. So altogether you have 6 products in this equation. Okay, in this case you get 6 products. Okay, again one has to be very careful about the stereochemistry. You have to check whether the product obtained is chiral or not. If it contains 2 chiral carbon atoms which are dissimilar, remember you will get 2 pairs of enantiomers. So that tells you that from this compound you have as many as 6 compounds. And then you have question number 23. Question number 23. If 4-methyl-2-pentene is 2-pentene, 1, 2, 3, 4-methyl, this is the compound. If 4-methyl-2-pentene, okay, this is a compound, is subjected to acid catalyzed hydration. Acid catalyzed hydration, it's again about carbocation chemistry, acid catalyzed hydration. You have H plus H2O, acid catalyzed hydration, or simply dilute sulfuric acid. It may be given like that, or dilute HCl. So protonation here will give you CH3, CH, CH3, okay, CH, CH2, CH3 with a positive charge here. That is one possibility. And suppose the protonation takes place at this point, you have CH3, CH, CH3, CH2, CH, positive CH3. So these are the carbocations. So these are the carbocations, and this carbocation, this particular carbocation can undergo a rearrangement, the hydrogen shift. It rearranges to a more stable carbocation, a tertiary carbocation, CH2, CH3 with a positive charge here. And if this rearranges, again the positive charge is on a secondary carbon. So these are the three possibilities. You have this carbocation, you have this carbocation, and you have this carbocation. There are the three possibilities. Do you follow? So from this carbocation, you can get an alcohol, CHOH, in which case this carbon will be chiral carbon and you have two products. And suppose this carbocation here, you have OH attached. OH attached means this carbon will become chiral. It's ethyl group, isopropyl group, OH hydrogen. And therefore from this also you get two products. Plus and minus you get. Two products are obtained. You have plus product and minus product. Whereas from this, an OH group is attached, two methyl groups. They are equivalent groups, and therefore this carbon is not chiral, and from this you will get only one product. So this carbocation will give to an alcohol which is optically active. It has a dextro and levo forms, and this carbocation will also lead to an optically active alcohol. You have plus and minus forms, whereas this rearranged carbocation will give only one alcohol. It is not chiral, and altogether you have 5 compounds. So a very good question. Now these are questions where the chemistry of carbocations and their possible rearrangements are tested. And also your knowledge about deciding whether a product is chiral or not. And if it is chiral, remember you have the dextro and levo isomers. Now this is something which is usually forgotten by students while answering questions. When they are asked about the number of isomeric compounds, they often forget about the stereoisomers, about the optical isomers and the geometry. When you are asked about the total number of isomers, it's very important that you count all the structural isomers and the stereoisomers. And if the question is specifically about structural isomers, of course, you consider only the structural isomers. If it is specifically about stereoisomers, you consider. But here, total number of isomers is the question. How many different alcohols? That means you have to consider all the possibilities, and you find that 2 plus 2 plus 1, you have 5 possibilities from the 3 carbocations. So first you have to understand what are the possible carbocations, and from each carbocation how many products are obtained. So that sort of thinking is necessary to answer questions of this type. It's a good question, and the previous question was also quite good. And now you have a very simple question in either on treatment with sulfuric acid. Of course, we have exceeded. It is, I had to stop at 8:20. Now 4 more minutes. I think in a couple of minutes we can finish 24 and 25. And either on treatment with sulfuric acid and sodium iodide. Sulfuric acid and sodium iodide means it will give HI. And either will be undergoing a cleavage. Undergoing a cleavage like this, HI, and at this part, HI, so that you will get 2 molecules of RI. But what is given is, you get only single alkyl iodide. That means these 2 alkyl groups are equivalent. Then only you will get a single alkyl halide. You will get RX only. If it are an ROR dash, you will get 1 molecule of RX and 1 molecule of R dash X. So it will say mixed ether. Now here you are getting only 1 alkyl halide, means it is a simple ether. The alkyl groups are equivalent. Now the question is, how many atoms are present in a molecule of EC? No other data is given, nothing is given as the molecular weight and all that. Only thing is that what is given is that this iodoalkane contains, the iodoalkane, that is the Ri, contains about 75% iodine. Now if it is about 75% iodine, then you will have to think of the possibilities, that's the point. So that is actually the mental exercise that you have to do, that is expected of you. If it is methyl iodide, the percentage of iodine, carbon is 12, hydrogen 3, and iodine is 126.9 or 127. It is 127 upon 130, 142. It is never 74.7%. It's much higher than that. So the next option, you take CH3CH2I, then you count the number of carbon atoms 24 plus hydrogen 5 plus iodine 127. You take the total 127 plus 5, 132 plus 24, that means 156. So 127 by 156 into 100. It is again not 75%. It is even more than 75%. And if you take the third possibility, CH3CH2, CH2I as the alkyl halide, you have 3 carbon atoms, 36, plus you have 7 hydrogen atoms, 7, and then it is 127, that is 134 plus 6, that is 140 plus 30, that is 170 is the molecular mass, so that the percentage of iodine is 127 by 170 into 100, and this is about 75%, which means the alkyl iodide is CH3CH2 CH2I, that's alkyl iodide, and therefore the ether is CH3 CH2 CH2 OCH2 CH2 CH3, that's the ether. Because it's a simple ether, you get 2 alkyl halides of the same molecular formula, you get a single alkyl halide, that is propyl iodide, and therefore this ether must contain 6 carbon atoms. 6 guys, pretty simple question, but the only thing is that you have to make a trial and error with the simple molecules methyl iodide, ethyl iodide and propyl iodide. You come with the answer when you take the case as propyl iodide. So simple question, I think all of you can answer, you can very easily answer the question. And now is a question where you are asked to distinguish between 1 propanol and 2 propanol. Both are alcohols. One is CH3CH2 CH2OH and the other is CH3 CHOH CH3. So routine question, not at all complicated, very straightforward question. 1 propanol and 2 propanol. So what all among these? You are given so many options, and how many of the options will work as method to distinguish between 1 propanol and 2 propanol? Let us check one by one. Copper at 25 degrees Celsius, the reaction is catalytic dehydrogenation, whereas this will give an aldehyde, CH3CH2CHO, and the secondary alcohol will give a ketone, and the aldehyde and the ketone can be differentiated by the tolerance reagent. Aldehyde will give a silver mirror with the tolerance reagent, whereas the ketone will not, and therefore A is correct option. And second is with the concentrated HCl and anhydrous zinc chloride, that is your Lucas reagent. We already said about the Lucas reagent, and Lucas reagent reacts with a tertiary alcohol to give immediate turbidity, with a secondary alcohol turbidity after say 5 minutes, and with a primary alcohol the turbidity very slowly. So the primary and secondary alcohol could be differentiated using Lucas reagent, that is B is the correct answer. Now what about C? Is potassium dichromate concentrated sulfuric acid, a powerful oxidizing agent which will oxidize a primary alcohol to aldehyde and the secondary alcohol again to ketone, and the aldehyde and ketone can be differentiated. So obviously the method C also works. And ozone followed by zinc dust and water, that's a reaction. Ozone followed by zinc dust and water, that's a reaction answered only by unsaturated molecules. So it cannot be used as a test here, but if you are given dehydration followed by zinc dust and water, it would have been okay, because dehydration of then also it will not be okay, because dehydration both will give the same compound propylene, and therefore the ozonolysis product will be the same. So in any case, ozone followed by zinc dust and water, ozonolysis will not work as a method of distinguishing between these two compounds, so it will not work. And then comes iodine and alkali. It is very, very powerful. iodine and alkali, you are reminded of the iodophone test. Iodophone test is a test which is answered by compounds which contain CH3CHOH group or the oxidized group CH3CO. So this group is there, okay. For secondary alcohol, for isopropyl alcohol, this group is there, but for normal propyl alcohol, you do not have this group. That means isopropyl alcohol alone can form iodoform. This methyl group is actually converted to iodoform on reaction with iodine and alkali, whereas normal propyl alcohol will not give iodophone test. So iodophone test is actually a test which works to differentiate between 1-propanol and 2-propanol. Then dehydration with concentrated sulfuric acid is not a test, because in both cases you get propylene as a product. So it cannot be used as a test. You are getting the same product in both cases. And reaction with ammoniacal cuprous chloride is a test where you apply the test actually to detect terminal triple bonds in alkynes. Terminal triple bond in alkynes. So that test will not work in this case. And reaction with acetic acid in the presence of sulfuric acid will give the ester in both cases. But it is not that easy to differentiate the smell of the esters, normal propyl acetate and isopropyl acetate, and therefore this also cannot be used as a test. A test is something which can be used to differentiate the compound rather very easily, not by any complicated procedure, but very easily. So of the reactions given, A, B, okay, A, B, then C and E. These four are methods which can be very successfully used to differentiate between 1-propanol and 2-propanol very easily and very successfully. And the question is, how many of the following methods can be used to distinguish? So of the various methods given, 8 methods are given, of which only 4 will work. Now, since for the JEE questions, the single digit answer questions are there, it is from organic chemistry. Very often they ask questions of this type. What are the possible solvolysis products? How many isomeric products are obtained during the monochlorination? Or how many products are obtained during the acid catalyzed hydration? Or how many of the tests can be used to differentiate between? Such questions are often asked as single digit answer questions in JEE main question paper. So we have seen some model questions. I think we have covered the entire things, but we have taken a little more time than what is allotted. But however, we could be happy that we could finish the discussion of all the questions. And thank you for patient listening, and goodbye.